Hi, I hope you guys are all doing well and staying healthy and hopefully have enjoyed the past long weekend. But today we're going to be working with section 1 from chapter 24, and it's over exponential equations. And I know you guys have worked with these equations in the past and in previous sections, but here we're actually going to be solving them. So we won't be working with as much of the graphing aspect, but we're going to be solving just like we have with quadratics and with linear equations in the past. And the steps are the same for almost every single question, which is going to help us out to get our toes wet before we have to solve them with logs and natural logarithms. So we're going to find the exponents or exponent first. And then we're going to move all other constants or coefficients to the other side. Does anybody remember what a constant or coefficient is? You would have probably covered this early in your algebra experience. But a constant is a number that's just tagged on. So if I say x plus 2, it's this, the 2, that doesn't have a variable attached to it. That's called a constant. And then a coefficient is always attached to a variable. So the 2 in this case is attached to the x, and that would be a coefficient. So what I mean by that is if we have 2 times our x to the negative 2r, we want to get rid of this 2 first, get it out of the way. That almost acts as a coefficient. Or likewise, if I had 10 to the negative 2r power, and I had minus 2 on the bottom here after that exponent, I'd want to move that 2 over and get it out of the way. Then from there, we're going to simplify, which you just saw. We're going to get it all to one side if we haven't already. Then we're going to make the right and left sides bases the same. And a base is, if I say b to the m power, the base is the b. It's the bottom, the larger number in an exponent. And then we're going to set the left and right sides exponents equal to one another. Now, you might be wondering how in the heck this works every single time and we don't ever run into problems. And the reason that this works runs off of the idea that if I have b to the m power equal to b to the n power, m and n have to be equal. In math, we have a phrase that's called if and only if, and that's what's actually between these two. And it means there's no other way. It's totally impossible for m and n not to be equal in this case. So we'll say if and only if. So we can use this concept to our advantage when we're working through these problems. It makes this easier for us because once we get those bases that are the same, then we can just cross them out and work with the exponents. So using these concepts that we just discussed above, we don't have any constants or coefficients. We can just start with our bases. So we see that we're working with a base of 10 on the left side, and I'm going to try and keep that consistent throughout so we get the same bases on the left and right. And 10, we can change into a base of 10. Can anyone remember what that exponent might have to be should we have a base of 10? I'm going to say that's 10 to the second power because 10 times 10, of course, equals 100. Then we're just going to bring our left side down, keeping it exactly the same. And our bases are the same now, so we set our exponents equal to one another. We'll say negative 2r plus 3 equals 2, and solve like we would a typical equation. So I'm going to go ahead and subtract my 3, get negative 1 equals negative 2r. So that means r equals 1/2, because a negative over a negative equals a positive. Looking at number 2, we're going to see when we work through the solving of exponential equations, there are different approaches. For example, when I think of 16, my brain immediately goes to a base of 2. But maybe when Miss Thomas sees this, she thinks of a base of 4. Or maybe when different students see that, they think of different things. And that's okay, because if it's solved correctly, we're all going to get the same answer, depending on just the process that we completed being correct. So if I'm going to use a base of 2, 16 in a base of 2 would be to the 4th power. So we'll say 2 to the 4th power, and we already have an exponent up there. So we're going to use multiplication in this case and just bring this exponent back down and stick it in parentheses. So we'll say 4 times 4p plus 2. What about 64? How can I make sure that has the same base of 2? Well, 2 to the 6th power is going to give us 64. And from here, we have the same bases, so we can just work with the exponents now. And we'll say 4 times 4p plus 2 equals 6. And we're going to do just distribution just like we typically would. We'll see 16p plus 8 equals 6. And when we solve everything out, we're going to see that p equals negative 1/8. So I said earlier that no matter what the base is, if it's correct, if a base is valid, that means that if 2 to the 4th really does equal 16, or if I take 4 to the 2nd, it equals 16, so I'm fine. As long as that's consistent throughout, we won't run into any problems. And I just want to kind of demonstrate that to you so you see that it actually does work out. So if I'm changing this, instead of a base of 2 into a base of 4, what would our 16 have to be in a base of 4? What would that exponent have to be? I said it just a few minutes ago. Good, it's going to have to be 2. And again, we're just going to keep the same exact exponent that was already up there, just this time in parentheses. And what would 64 be in a base of 4? You can go ahead and pull out your calculator and kind of guess and check for a second. It's going to be an exponent of 3. And again, our bases are now the same, so we can cross them out. So we'll say 2 times 4p plus 2 equals 3. And again, we're going to solve through it the same way that we did before. And again, we're going to see that p equals negative 1/8, which is exactly what we were expecting to see. So that means that no matter how I choose to solve it, totally independent of what bases I use, I'm still going to get the same answer. Okay, looking at number 3, what's the major difference now? What do you see is different between 1 and 3 and 2 and 3? We're working with fractions now. And can anybody remember how we can get a fraction using exponents? So say, for example, if I wanted to use a base of 2 here, how could I show 1/2 with a base of 2? What would that exponent have to be? It would have to be negative 1. So that negative 1, that negative denotes that now we're going to stick a 1 over top of it. We're going to change it into a fraction. So if I make it a negative 1, we're still going to bring that down, that exponent that we see above, and it'll be times x plus 1. And the same is true of the 1/4. How would we typically get 4 with a base of 2? We would take it to the 2nd power. Well, we're going to do that again, only this time we're going to make it negative to denote that it's changing into a fraction. We're making it a reciprocal. And again, our bases are the same, which is nice. We can just cross those out and just work with our exponents now. We've got negative x minus 1 equals negative 2, and solve. So x is going to equal 1. Now, number 4. How is number 4 different than number 3 if we're looking at that equation? What's the major difference? Good, we have multiplication now. And remind me, when we were working with our exponential properties before, what happens to our exponents if I had 5 to the 6th times 5 to the 4th? What do we do with these exponents if we're doing multiplication? Good, we're going to add them. So we're going to use that same exact property here to solve this equation. And we're going to begin first by looking for exponents, and we see that they're kind of strewn throughout. And now we're going to start to convert our bases. So I see a 5, which I think will be easy to convert into a base of 5. So if I have a base of 5 that I want to work with, how can I set that equal, or how can I make 1/5 into a base of 5? Good, I'm going to use a -1 as the exponent because I want to create a fraction. Now, what about that 125? How can I make a base of 5 into 125? What exponent would I have to have? Good, I'd have to have 3, because 5 times 5 is 25, times 5 more is going to give us that 125. And again, I'm going to bring down that exponent that's already up there. Well, if 5 to the 3rd was 125, how do you think I can get 1 over 125? Good. I'm going to add a negative to my exponent spot. And now our bases are all the same, which makes things easier for us. Now, typically, I add the exponents after I cancel out the bases. Some people choose to, after they have the bases, add them before they cross them out. It's kind of up to your preference, what you like best, but I'll demonstrate this way first, at least. So plus 2z plus 2 plus -9z equals -3. And I'm going to simplify on the left side before I move stuff over. 9z, 2z, -7z plus 2 equals -3. Now I'm going to move this 2 over. -7z equals -5. And we're going to divide that -7 over. So c is going to equal 5/7. And you can see I canceled both our negatives because we would have had a negative over a negative. And that's how we solve. If you have any questions or are confused about specific steps, feel free to come and visit us in our office hours and say hi or ask any questions you might have. But I hope you guys stay healthy. Bye.